Okay, so welcome everyone back to an exciting session. We are having very interesting conference since the morning, and we'll also have tomorrow a lot of exciting sessions up there. So this particular session is dedicated to an emerging paradigm of quantum-like modeling in social science, which is an exciting paradigm. It started about 1 decade or so earlier, and it is really growing stronger. And we have today with us pioneers and frontier researchers in this particular paradigm. I will be introducing the speakers over time, but let me also just have a few words on quantum-like modeling before we start. So myself, Dr. Sudip Patra from JSGP, and also Complexity Economics, Applied Spirituality and Public Policy Center. So quantum-like modeling has really nothing to do with genuine quantum physics. So that is one bit of misunderstanding we may have. So quantum-like modeling is rather more into mathematical modeling and building upon different conceptual and philosophical ideas from natural science, mainly, which has been widely used in quantum theory or quantum field theory, and then extending that to decision sciences, economics, finance, and other social sciences, and also trying to see that what kind of practical and policy implications that might have. I remember that when I was still completing my PhD, Emmanuel, Professor Emmanuel Haven, who is like our first speaker of the panel, one of the pioneers in quantum-like modeling. So he was very kind to communicate to me and introduce me to this wonderful field where I'm working now. So let me turn to the first speaker of our evening today, Professor Emmanuel Haven, who is a chair professor in finance at Memorial University, Canada. He has been one of the pioneers in this field, along with Professor Andrei Krenikov, who is based in Sweden. They came up with a seminal book in quantum-like modeling, Quantum Social Science, which came out in 2013, Cambridge University Press. And actually that book created a lot of attention towards this particular regime, and many researchers from different fields started coming into. So we can consider that as to be a milestone. Later on, certainly, Emmanuel has really edited a lot of special editions in many noted journals, for example, Quantum Reports, then the Journal of Mathematical Psychology, which is a very important journal in this area, Journal of Mathematical Economics, Royal Society journals, and so on. So we are really glad to have Emmanuel at our panel. He has been associated with us in different projects at CASP2, as I just mentioned earlier. So over to you, Emmanuel, and please take the stage.
Thank you so much, Sudip. Maybe I should start trying to share the screen first, no?
Also, hi, Sudip, hi, Emmanuel, Shivangi.
Hello.
Yeah. So the previous session is still on. I think it's getting. So I think I saw Professor Orel over there, and I might. So there might be some of the participants who will join in late.
Okay, but we
can start.
yeah,
We can start the session.
yeah.
Right?
Yeah, that's no
So
problem.
I must say that Shivangi is our superstar. So she arranged the whole conference with Gita. They are
Yeah.
like our stars.
Yeah. Shivangi is. I know. I've been in contact with her.
Yeah,
Also.
she is very active.
She's very good.
Yeah.
So Sudip, first of all, thank you for the extremely overpowering introduction, which I really don't deserve. But just to let you know, indeed, I mean, I've been associated with Sudip and Dr. Naresh Singh, and also Dr. Chakraborty. And also, I've also connected with other colleagues in India, very good co-author, Dr. Vikram Atalai, with whom I work also. And it's really a pleasure to work with people from your country. It's very enjoyable. Sudip was very overpowering in his message.
Just a minute.
Go ahead.
Yeah, just one reminder. Our presentations might be about like 20 minutes, and then
Yeah, it will not be so long, Sudip. No. So indeed, Sudip, I remember when he was working on his PhD at the University of Glasgow. I remember it was actually, Sudip, it's true. It was very brave of you to work on a PhD in such a very, very new area. So the amount of courage you had to really exhibit in a PhD defense and bring forward those important ideas you had, I mean, that goes a long way in telling, how, there's a lot of people who would not venture into this at the PhD level because they would be so afraid to get knockbacks all over the place. But you did it, and you did very well, right? I mean, you passed it extremely well, and then afterwards you started doing research and publishing very well in it also. So you're certainly, I mean, you're talking about me being some star, but I think you are definitely a star. That's pretty much confirmed, I think. So is there a quantum social science revolution? That's the question here. Let me just see if it works. Here what Sudip said was probably right, but Sudip, maybe I have misunderstood you. So quantum-like modeling or quantum-like applications in social science, I think if Sudip, if I got it, but please correct me if I'm wrong. I think you mentioned this is not really physics. It's really just using formalisms, being very upfront about it, being very explicit about it, that you use those, giving them the correct names, right, as you should. Because we know of other disciplines that sometimes they will borrow things and they won't give the name of origin, and right, but this is really an area of work where I think we are very upfront about what we are doing, and we're very upfront about using the terms as they are defined, and we are not hiding it, right? So therefore I also would dare to say one opens up all the gates for criticism from people from outside very easily. So people who know not so much about this, or people who have a bias against physics, or people who think that quantum is completely ridiculous in terms of the area we are applying, well, I mean, it's open, right? We are an open house. We are talking about hermeticity, unitary transformations, and we use the language, and we are very open about it. And if people want to attack us, they can absolutely do so. There's no issue here. It's not the first time, as people in the audience will know, it's not the first time, of course, that physics is used in social science. We know the econophysics movement. Professor Chakraborty is a star in that area. Right, he studied under the best people in the area. So this is a very, very well-established movement, which has basically used statistical mechanics in finance and economics. But I always would like to contend or argue that it's maybe not a movement which really has been all that important in terms of modeling as such, I think. That's my understanding. Now, I mean, people who are very well versed in this area may just completely disagree with me, but that's sort of the impression I have. Of course, in finance, as Professor Orell, for instance, would certainly be able to confirm, right? We know that, for instance, option pricing is basically a physics-based theory, of course, not quantum mechanical as such, of course, but it has as a backward Kolmogorov PDE, so it has, right, a heat equation, it has all the traits of what an undergraduate physics student would recognize right away. And I can testify to this when I taught a quantum-like course in the physics department back at the University of Leicester, where I was before. Basically, the students in the audience recognized right away the heat equation characteristic of the Black-Scholes PDE, and they kind of knew how to solve it, and they were fine with it. So I mean, of course, you have to be careful. If you're from outside of finance, you could get the impression that a lot of finance is maybe physics-based. That's not true. I don't think so. Sudip, I don't know if you agree or disagree, but I don't think that's the case. I mean, the superb example is the Black-Scholes one. I mean, this works, right? There's a phenomenal theory in finance, but which is basically I think, divorced from economics, and it's, I mean, you can put it in finance, but actually it has really connections with physics. So, but it is a very, very, very successful theory, right? So let me just talk a little bit about classical mechanics. What we have, one of the, there's an enormous amount of stuff which has been done in classical mechanics and applications to social science. So I'm certainly not going to survey this here because I don't have time for it anyhow, and I wouldn't be able to do it properly anyhow. But I'll just have a quick look at some of the classical mechanics applications, and then we'll step into quantum mechanics. So what we have in economics, for instance, is when we start with in economics to teach basic microeconomics, what we're going to do is we're going to talk about utility functions, right, which are measuring preferences. And that's basically the first thing I want to talk a little bit about and show you how classical mechanics can come into this. This appeals to the idea that we actually may well be modeling now with classical mechanics in economics. That's that paper, which Sudip, of course, knows very well, by Bilal Baki, which I think is still a very beautiful paper, which really goes to the root of basic microeconomics and actually just expresses it in physical terms, and shows what sort of augmented understanding we can get via the introduction of those concepts, those physical concepts. Okay, and then maybe we'll, if we have time, we can talk a little bit about opportunistic decision making, and then we can talk a little bit about quantum mechanics and maybe the reality between the building blocks of quantum mechanics and maybe an expanded Newton law if we have time. So if I want to start out with just economics and just simple utility theory, then that's what we have there is the relationship, if and only if relationship between the preferences of two objects, x preferred over y, and the existence of utility function u, which if x is preferred over y will give you the utility of x to be bigger than the utility of y. So that's what we learn in basic economics, and the key thing here is the if and only if relationship. So if you can graft classical mechanical IDs in this very simple ID, well, it's not a simple ID, right? I mean, finding a utility function is not all that easy, right? But if you can do that, then you really look at basic modeling within economics with the use of statistical mechanics. So what we do in economics is also what I have here, right? So consumers will maximize the utility function subject to budget constraint. I think maybe you've heard about that. And so you're going to get from that then demand functions, right? And here, for instance, you have a demand function, which is inversely related to the price. And you can also have supply functions where that's going to be this in function of the price, not the inverse, but right, the opposite. So you postulate that in economics that the interplay of supply and demand will determine stationary prices of commodities. And then the paper from Bilal, I know that Sudip knows that paper very well, is really beautiful because it will actually define, actually that's wrongly spelled here because I should have three horizontal lines, will define the potential as the sum of the demand and supply. So the potential function, so we basically, what he does is he's introducing a Hamiltonian framework where there's a potential function as a kinetic term. I'm not going to talk about the kinetic term, I think. But he is really introducing this within a probably the most basic framework of microeconomics. So this is a paper which I really think should be cited much more. And like Sudip says, but this is of course in classical mechanics, but like Sudip says, maybe there's more and more interest in it. I would have to talk to Bilal to see how in terms of citations, how much uptake he's getting on specifically that paper. I haven't checked it actually. But I think it's a very nice paper. So basically, the result he gets out of this is this result here, is that when he minimizes the potential towards price, he gets that equality relationship here between the change of P on demand and the change of P on supply, and that just offsets. And that's exactly what you want, right? You want a sort of equilibrium relationship. So that is a little figure he has here, right? Oh, I'm so sorry. That's wrong. Sorry. So if you look here at the, sorry, this, I don't know why this is not working, but okay, if you look at the minimum of the potential, that's exactly what you're going to find is the equilibrium. And then you can talk about the area around the minimum and then infer also some economical IDs using that expanded framework. And that's not to talk only, we only talk just about potential here. So this I don't know if you see that minimum though. Anyhow, it seems to be obliterated every time with something else here. But that's just only to talk about potential. So we're not talking about the kinetic part, right? In his paper, of course, he does. And if you haven't read the paper, please have a look at it because it's a very beautiful paper. So that's one example of statistical mechanics going into economics at the very core of very basic microeconomics, but using a modeling approach, basically. You could do other examples of this. For instance, what I call opportunistic decision-making, where you have a financial payoff function, right? So you have a financial payoff function which maps positive non-zero reals into reals. You buy a contract. This is for real, right? So this is not a theoretical thing. So you have a contract which stipulates your details of payoff function, and then you buy such a payoff function, and you hope that it will realize the payoff in the future. And you only know this, right? This bit here. So upon where the underlying asset will position itself after you bought the payoff function. So you don't know this in advance. So you could think of a situation where you have, for instance, a payoff function which is constant, and you could just say, okay, well, in that case, I mean, basically the payoff function in terms of return should give you the risk-free rate of return, right? Because no matter what happens, you get a payoff of W, right? So you can fix the payoff at the level W in such a way that the return on the payment is the risk-free rate. So what you could do is now you could actually here have the payoff function to be a potential, constant potential function, and actually have a Lagrangian framework you could introduce in here. And then you could actually bring in the ideas of no arbitrage also. There's absolutely no problem to do that within that sort of framework, like in this case, for instance, Lagrangian framework. But of course, there's nothing quantum mechanical at this stage here. So let's go a little bit more into quantum mechanics. I always like to bring back, and Sudip knows this also, of course, that in fact, those discussions for people from outside the area, those discussions of quantum, especially complementarity, for instance, in quantum mechanics, and the idea of using it in psychology, was really already a discussion which happened between two huge names in the sciences. Wolfgang Pauli, the Nobel Prize of, I don't know, Sudip, did he get for the exclusion principle? What did he get the Nobel Prize for? I don't remember.
Yeah. Exclusion.
Yeah. So, and then and Jung, Carl Jung, who was huge name also in psychology. So they were really interacting with each other in the 1950s already, right? And this is not the only example, by the way, right? There are other examples. But that's just to tell you, right? So that they were really already thinking about possible links between ideas from quantum mechanics and psychology. So complementarity, as some of you will certainly know, is the impossibility to distinguish between behavior of an object and its interaction via the instrument observing it. That discussion of the 1950s is contained, if you want to have a look at the book by Meyer, 2001. It's a beautiful book. There's a lot of nice ideas here on how Pauli, because Pauli was very difficult, from what I understand, he was a very, very extremely rigorous person. And very difficult and extremely difficult to deal with. So I mean, it's always funny to see that people like this, who have those enormously high standards, are actually getting into discussion, for instance, with Carl Jung on that topic. I've always been amazed by that. Right. So, of course, it is true, as Sudip also will say, we are not claiming that anything here is quantum mechanical in macroscopic environments. I mean, that's not what we're claiming, right? We're not doing that at all. So, and that's what I'm saying here, right? We're not implying that the macroscopic process in study is quantum mechanical. So, quantum-like, what we wanted it to be defined as in the handbook. We had a handbook, Andre, myself, with I forgot the publisher. Palgrave, I think, Palgrave Macmillan, yeah, I think, yeah. And there we try to define what quantum-like is. So we look at a deeper level of information. There's a wave as a carrier of information, maybe also a deeper level of uncertainty. I'm not saying that I feel uncomfortable about reading this now. No, I don't. But of course, it still is difficult to define, right? And to pinpoint it. It's hard, right? I mean, like, for instance, when I say here, risk as measured by quantum potential wall distance, okay, that's an application we did also about using estimating quantum potential. Okay, so it's an interpretation. There was nothing really definite about it at this stage, not yet, but maybe it will come, right? So there's some important papers for those who are new to the area. Certainly have a look at the paper by Polina Konikova, by certainly by Sudip. Also the paper he has with Polina in Physica A on asset trading. Sudip's paper with Professor Rooney, which is a GBS working paper. I mentioned here Anirban also, but not Anirban. The network geometry paper is definitely not contact. That's a very beautiful outgrowth of econophysics. Well, it's within econophysics, but it's a star area of econophysics. Networks are really the shining area. I think that's true, right? Like the sort of shining armor area of econophysics is networks, right? And then, of course, in Poultis and Emmanuel Poultis and Jerome Busemeyer have done very nice work. For those who are interested in psychology and application of quantum-like formalism in psychology, I mean, those are really key authors to look at. There are many other ones, but certainly Busemeyer, Jerome Busemeyer, and Xing Wang, and also Emmanuel Poultis are really star people. I mean, I have to also mention my co-author Andrei Krennikov has done phenomenal work in this too. So the wave function is just that basic building block in in elementary quantum mechanics. And of course, this is an eternal discussion in the foundations of quantum physics. Is the wave function corresponding to an underlying reality, or does it represent partial knowledge about a real physical property of a quantum system? And there is an enormous amount of work which has been done by Sheldon Goldstein, right? He, for instance, wondered whether the wave function, does it represent information, or is it an independent observer independent reality? If it is objective, right, does it represent a concrete material sort of reality, or a different, entirely different, perhaps novel nature? If it's information, right, is it presumably concerned directly either with mental events or more likely with the behavior of macroscopic variables? I mean, I'm not a physicist at all. Sudip is much more of a physicist than I am. I don't know. I just don't have a clue. So I better tell you in advance because I really don't know. But it may well be useful to settle on a meaning of the wave function first. Use it as a sort of elementary device within our quantum format. And here is a very simple idea, which I always teach the physics students in the course I teach in the physics department on this, where you look at the superposition of ID states, right? Here they are, right? All those, I mean, we talk about cats and bras in quantum physics. I mean, this is an example here. And you can think in the same way of value states and price states. So you can talk about a superposition of value states, which gets you to a price state. And then here you see here, the square of AI, that's the probability of each value to occur. And here you could say, well, of course, you could certainly say, I mean, one of the things you could certainly wonder about is if the ID states are really linear independent. Are they basis for a space? Do you have an additive inverse? What would be the meaning that you have, right, the orthogonality here, which is 0? Assume that you make a measurement, right, and you have value 2 occurring with a 2 squared. That's your value or your probability value. Then the question becomes, what type of probability is this? I think. I mean, people may disagree and say, Emmanuel, you're wasting your time. But you could say, there's a very nice paper by Ballantyne on objective and subjective probabilities in quantum mechanics. You could say, well, is that probability, the A2 squared, propensity-based probability, right? So that the probability that the next measurement will yield value 2 is given by A2 squared. Is it a frequency-based probability? That is, in the long run or in long term of similar measurements, that fraction value 2 should be close to the value of A2 squared, right? So it's not exactly the same stuff, right? So is it a subjective probability, right? my degree of belief. Oh, this is getting complicated. Huh? I don't know. When I read this, I say, oh man. So my belief that the next measurement will yield value 2, value sub 2, is given by A2 squared. Okay, I don't know. Right. So so there are questions there. Now I have to say that if you want to be if you're interested in the psychological aspects of using the quantum formalism, I mean, it's really important to look at the papers by Andrei Krennikov and Jerome Busemeyer, especially if you're new to this. I would want to pinpoint to the paper which I just picked up here on the QQ equality. So the QQ equality is really, I would say, a milestone in the decision-making area, which is using the quantum formalism. If you want to know more about it, please write to me or write to Sudip. There is a generalization of the QQ equality, which is given by a paper by Andrei Krennikov, which actually puts it as even at a more general level now. And that's milestone stuff in the decision-making area. So if you wanted to have a good idea of how quantum decision-making can be actually, this going a little bit beyond just saying I'm using the quantum formalism, I'm using quantum probability to explain some deviations from decision-making with some interference, the QQ equality is actually really giving you, I would say, a pretty intense flavor of decision-making as being quantum. That's another, you're at a different regime here. So I started out this talk saying, guys, we're just using formalism and that's it. QQ equality gets us in a terrain where we say, okay, guys, maybe there's really something going on here. And it's nice. And it's generalized by Andrei Krennikov, so the latest paper by Andrei Krennikov with the quantum measurement approach, which is very interesting. But if you want to know more about that, I can definitely send you the references. Okay, so I'm just going to finish up quickly with my usual story on using Bohmian mechanics in finance, where I still believe there is a lot of interesting things which can be done. Here, I have to be a little bit careful because there's work by Yves Couder and Emmanuel Faure who looked at what they sort of looked at the macroscopic pilot wave system. But you have to be very, very careful that you don't infer that because there is a sort of macroscopic pilot wave system that this therefore means that some macroscopic events show quantum behavior. That's not, I think, the message of the Faure and Couder. But basically, the idea here is pilot wave theory. So basically, it's a Bohmian approach to quantum mechanics gives you a sort of a classical mechanical trajectory flavor of quantum mechanics, which typically in ordinary quantum mechanics you don't have. So you have a multiplicity of paths, and those sort of ideas of multiplicity of paths could be used within finance. So you could look at what I've tried to sort of argue for as a sort of a Bohmian path coming out of an extended Newton equation, which is not only just a negative gradient of V, real potential, but the negative gradient of two potentials, V and Q, Q being the so-called quantum potential, which is an object, which I don't know, Sudip, what you can say about it, whether this is really a potential or not, or what sort of physical characteristic it has, but it comes out of basically using the polar form of the wave equation in the Schrödinger equation, and then you have a continuity equation and a Hamiltonian-Jacobi-Bellman equation, and you have that term there which appears and which is then that's the so-called quantum potential. So basically you extend the Newton equation, the second law, FMA, into the force is now going to be geared not only by the negative gradient of V, but will also be added now in by the negative gradient of Q. Our argument here is that we have different types of information, which, well, it's not different types of information. I think what we are trying to capture is that if we have public information, we capture different effects of that public information via V and via Q. And that's something I'll just stop with here. What you can see, for instance, here, what we did, my ex-PhD student, Chen Chen, who is working actually in the finance industry. That's something we did here, where you can see there's this the brownish. I don't know. I'm a bit colorblind, so I think it's probably brownish. The one which has this sort of minimum. So the how do you say that? The broken line, I think, or the line with little spaces in it, right? Has that minimum here on a daily return, on volt return, and that's as a real potential, which is what you would expect, right? On a daily return, you have to be very close to zero, of course, and then you have that that blue line here, which is a quantum potential. So it seems to measure something different. I mean, the same public information, because it's of course daily return, so you get everybody can infer that from data, right? But you're sort of measuring something different. And you know, Andre had some very good ideas already back more than 10 years ago, easily, on how to interpret this quantum potential from a pricing perspective, how it would be seen as a sort of a force which restrains prices to go outside of certain boundaries. And it actually is a bit looking like that. In fact, if you look at, for instance, how you would draw the forces on the basis of those potentials, actually you will see that actually they are very high, very steep. The gradients of the forces are very steep at the balls. Okay, and they coincide, of course, and like they coincide here. Right? Okay, so by the way, also I forgot to tell you. So Reza Jafari actually was one of the first. I think he was the first who actually looked at real data and published this in Europhysics Letters in 2015. He really looked at real data, inferred quantum and real potentials, and then came up with a theory of what those things were really measuring in reality. Okay, so pitfalls on all of this, and Sudip of course knows those too. Are particles humans? Well, we're not saying that really, but I just would want to say one thing though. When I give talks like this in social science environments, that's the sort of thing they will say, oh, particles are not humans. But then I retort back and I say, look, have you looked at what the underlying Brownian motion is, right? In option pricing, it's a Brownian motion. Well, Brownian motion was really something which was obviously formalized by Einstein, we know that, but which was actually used already in 1900 by what's his name now? Oh, well, the student of Henri Poincaré, Bachelet. Right? So you have really a process which is very well known in physics, which is used as the underlying, right, to describe the underlying stochastic process of an asset, whether it's a stock or it can be other things, but over time. So we have to be careful not to always want to say, oh, well, you shouldn't be using physics in social science. But sorry, I mean, you have a very good example here of a very successful theory where that has happened. And I contest, I would like to really say that if you look at decision making and the applications of quantum probability in decision making, that the QQ equality and the generalization of it really show you that there's a bit more going on than we just thought, than just plainly using a formalism to explain things. There's a bit more going on there, probably. That's a milestone, right? So in decision making. In finance, we have not seen a milestone yet at this stage. And there are issues, right? For instance, I talk about non-hermeticity. Of course, but non-hermeticity, I know quantum physicists will say non-hermeticity, what do you want to do with this? But there are some very good people who have looked at non-hermeticity, right? I forgot his name, a very famous mathematician from the US who, very well-known mathematician who did actually work on
Bender, Carl Bender.
There you go. Exactly. Thank you, Sudip. Right. So there are ways to, right? You have to be careful with this. So we use the word quantum like, I mentioned that also. So I think that's where I want to leave it for now. So as Sudip said, there are many more publications coming. It's very thriving. It's very, we have very nice people coming along. David Orell is, for instance, an example, and there are many other ones. So it's a very growing area, and I think it's moving from strength to strength. So that's sort of what I wanted to say. I would like to thank Sudip and, of course, the university for organizing and giving me the chance to talk to you in India at what's the time here? 10:40 in the morning, which is perfect timing, which is getting very late for you. But thank you so much.
Thank you very much. Yeah.
How do I go back to?
I think
sorry.
you have to just stop sharing.
How do I undo it though?
Stop sharing. Stop sharing.
Stop sharing. Oh my. Where do you do that? Huh? Would you know where I press for this? Or?
You go to share screen and then I think stop sharing. Shivangi.
Oh, okay. Here, maybe here.
Yeah, on Zoom, I think you'll get it, no? And I think if it's, or maybe press escape to, if it's not full screen, no? Or is it?
Oh yeah, it's
Yeah,
gone. Yeah.
Yeah.
Okay. Thank you.
Yeah.
Thank you.
Thanks a lot for this very
My
interesting.
pleasure. My pleasure.
So it's a very interesting overview of quantum-like modeling. So let us see if we have some questions from the audience. Anyone, please, maybe just a couple of questions before we move on to the next session, next part. Yeah, I think Shivani, yeah. Go ahead.
Good afternoon, Professor. Good afternoon, Professor. My name is Savani. Firstly, I just wanted to say I really enjoyed the presentation that you just gave. It was very informative. Thank you so much for taking the time out for this. My question is, do you believe that in the evolving study of application of quantum mechanic models to things like politics, do you believe that there's any future for quantum-like modeling in the field of political economics?
Yeah. Yeah. Are you saying political economics or political science, Sivani?
I think political science, yeah.
Yeah.
Professor, my question was, do you believe that there's a future for quantum-like modeling in the specific field of political economics?
Yeah. I think, Sivani, I think where we have a little bit more problems in political science is because you have to work with what Sudip also knows very well about those open systems. And the open systems are difficult things to work with, right? So that's this whole KSL dynamics approach. I don't know. I do worry that because of, I think it's a much harder setup. And it looks like you're kind of obliged to work with open systems, so you can't work with isolated systems, right? The Schrödinger system is an isolated system, so there you have to work with what we call open systems, and that's, I think, much harder. And I don't think you have a choice other than to work with open systems. So I don't know. I mean, it seems to me to depend on. So that's one thing. The other thing, of course, I forgot to tell you, is that of course you could work with approaches of quantum field theory, where you can start counting, but the Hamiltonians are so complex in those areas. They are so mightily complex that I think it's, I don't know, very incredibly hard to use. Sudip, please go ahead.
I can just add to that recently some good works have been done there. Emmanuel has worked with Polina on voters preference pattern, though that is a bit different kind of modeling. But for open system modeling, I think Fabio Bagarello has worked quite well.
Yes, he is the expert in the area. Absolutely.
Yeah. So he has worked with operator algebra.
That's right. Yeah. Oh yeah, he is. Very good point. Yeah.
Okay, so any other question from the audience? Okay, so maybe we can just keep on thinking, and we can send the questions later on.
Absolutely, with pleasure. Yeah.
So
thank you,
Sudip.
Thank you all attendees for your questions. Thank you.
So let me then. Thanks a lot. Thanks a lot. So let me then turn to my own bit. Though my presentation would also be an introductory presentation on quantum games. And then I will turn to Cheshta, our colleague, and Cheshta will actually play two recorded versions because unfortunately we couldn't have the other speakers live due to time zone problems. And I will definitely introduce those eminent speakers after my short presentation on quantum games. So let me start sharing the screen. Otherwise, Cheshta might help me, but let me share the screen. Is it visible? Okay. Okay, so let me just have a brief overview of quantum games. This is another quite interesting paradigm which has started and basically builds upon quantum-like modeling, but also takes it a bit far. So exactly what is it about? We will look into this. In my
Sudip, to just
Yeah.
sorry to disturb you, could you make it full screen? Because
Okay. Is it fine?
it hasn't yet become full screen for us. Maybe.
Is it coming? Because I can see full screen.
Maybe there's a lag. Anyway, I think if you can see, then but I'm not sure. Cheshta, is it full screen for you?
No, professor, actually.
Uh,
So could you just I think check again?
okay, let me continue
Yeah,
somehow.
otherwise we'll continue.
Anyways, I will be definitely sharing the PPT. Yeah. Okay, so actually these are the few things I would like to talk about. First of all, what are quantum games? And then certainly, as Emmanuel stressed a lot on networks, then let me get a bit into quantum Bayesian networks, which have been quite interesting things which have come up. And then certainly with my co-author, the eminent quantum physicist, Professor Patra, I have been working on this particular area for some time. So maybe I can just briefly describe a new game that we have designed and some question answers, definitely. Okay, so are you able to see it? Okay. So now let me actually go to the other slide first of all, and then get back. So you see that quantum games are actually evolving in at least 3 directions, and that is quite interesting. One particular thing is, one particular direction is the way how cognitive scientists or cognitive psychologists, Emmanuel also referred to them a lot, they look at games. Definitely, they are really not, followed by the classical game theory predictions in a way. Rather, they would like to see real people playing games. So, the real agents, they are strategically interacting with each other under contexts like uncertainty or ambiguity. And then based on their real behavior, they would like to describe their behavior basically. So again, since we have a lot of evidence as of now, as Emmanuel also mentioned, for the last 1 decade or so, that and even going back to behavioral finance and behavioral economics literature from 70s, even earlier to that, 60s, that often people do not behave like a well-behaved Boolean agent, as we can say, or a Boolean rational person. So maybe quantum-like modeling, which is based on a different kind of mathematical setup, which I will get back to, that might give a better overview of the deviations. So why those deviations arise, and definitely, as Emmanuel also mentioned, there is something called as interference terms. So those interference terms might be able to describe better how real people behave in game theoretic scenario and so on. And therefore, the empirical literature is very much based on finding out those phased terms or those interference terms. There are algorithms written about it and so on. So that is one particular perspective, the perspective which a cognitive scientist would take. The second perspective is very interesting. That is where quantum physics comes in really. And that is how games are really designed. So it is not like a passive observation of real players playing game, but where you are really trying to design the game by using certain kind of quantum devices. So say, for example, either quantum computers or say quantum circuits. These are various interesting fancy things. But as with Professor Ghosh, we have shown that more simpler systems might also do. And what happens is that players are sharing this particular physical resource among themselves, and they're trying to do certain kind of operations on that physical resource. And those operations actually give rise to their strategies. And those operations actually give rise to the final state. which give them some kind of payoff. Now, this is what is known as to be quantum game design, which is really where you are designing the game. And why it is quantum, really quantum, because the system that you are sharing among players, they can exhibit certain genuine quantum features in them. For example, entanglement, superposition, and so on. And since these are genuine quantum features, so ultimately the probabilities which are calculated based on these features, they give certain kind of equilibrium outcomes, which in most of the cases, it has been shown that they are like more superior to the classical counterparts. Not always, but in many cases. So this is the real quantum game design coming in. So where quantum physics is really needed to understand. So one is quantum-like approach, one is quantum game design. The third thing which we really don't need to interact so much with here is basically the other way around. So if you go to quantum foundations, there are some very recent happenings where physicists would actually like to recast quantum mechanics in a game theoretic way. So they would rather like to recast quantum mechanics in so-called non-Nashian games, so which are like non-classical games with contextuality built in it and so on. So I just mentioned this because this shows that there's a very interesting interplay between game theory and quantum theory at various levels. So that is the whole thing. So actually with Professor Ghosh, the paper that we wrote and which is going to be published very soon, that is basically about designing the game. Earlier, we also wrote a paper on quantum-like modeling in game, which came out earlier. So let me then go very briefly to the mathematical modeling part, which I would just like to kind of elaborate on certain points, not taking too much of time. You see that as Emmanuel mentioned very well in his presentation, that what happens is that in any kind case of quantum-like modeling or quantum game modeling, whether you use quantum physics or not, the basic mathematical modeling is about Hilbert space. Now, Hilbert space is complex linear vector spaces where which are norms are defined on that and scalar products are defined on that. So you can brush up your kind of linear algebra a bit. Now, Hilbert space, as opposed to, say, for example, real analysis, which has been used in classical game theory or neoclassical economics so much, that is rather, in a way, the basic tool for doing quantum-like modeling. It is not surprising because you see that Hilbert space has nothing inherent to do with quantum mechanics. Basically, physicists will also tell us that quantum mechanics can be written without Hilbert space also. There are other ways of writing quantum mechanics, might be more cumbersome. Hilbert space is more kind of cozy and more kind of coherent. Now, Neumann, John Neumann, another prodigy in mathematics and one of the founders of Copenhagen.
Sudip, can I interrupt you for a second? I think your slides are not changing for all of us. So I think could you just share it again?
Okay, now is it changing?
Yes, we can see it now.
Okay. Yeah, I think it.
Yeah. So we couldn't. Yeah. Okay, great. Thank you.
Okay, nice. Fine. So yeah, actually, yeah. So I was just telling you something about history. So John Neumann, who was one of the founding fathers of Copenhagen interpretation of quantum mechanics, mathematician. So he started using Hilbert space representation in quantum mechanics. But then later on, he used Hilbert space setup for other areas of science also. For example, optics and classical mechanics, and Hilbert space modeling became its own literature. So it is not inherently related to quantum mechanics. That is one point. So here what we do is basically we represent any particular state as a ray in the Hilbert space or as a vector in the Hilbert space, which follows various properties of the Hilbert space. Now, what is this particular state? As Emmanuel rightly mentioned, wave function. So we would like to be more pragmatic about it. We are not saying that wave function is the physical reality. We would just like to take a more kind of information theoretic version, for example, that wave function in a way, or the state, for example, which is a ray in the Hilbert space, that might reflect your knowledge about the real world. So it is rather more like a Bayesian way of looking at the world, but from a quantum view. So often called as to be quantum Bayesianism or cubism. And then there are certain interesting properties of that. For example, that state can be written as a kind of superposition of basis states, which is linear algebra basically. So ket phi, for example, is written as alpha ket 0 plus beta ket 1, where 0 and 1 are the computational basis and they are the basis states, such that alpha square plus beta square equals to unity. That is the completeness condition. Otherwise, it won't suffice as probabilities. Remember one thing, that alphas and betas are just the probability amplitudes. They are not the probabilities. And that is a very important distinction between classical model and quantum-like model. So only when we square them, once the measurement happens on that particular state, then only they are in a way mapped to classical probabilities. So alpha squares and beta squares can act as probabilities, but not alpha and beta. They are just probability amplitudes. And that is the main, one can say, a mystery of quantum modeling. This is called as to be the superposition state. And superposition is basically the basic uncertainty description. So say, for example, if you think 0 and 1 are like kind of happy and unhappy states of an agent, or a yes or no state of an agent. So basically the superposition would mean a kind of ambiguity state. So before the, say, interaction happens with the environment, or there's some kind of measurement of that or updation of that state of belief, in this case, it will remain in this uncertain state. And then once the measurement happens, often called as to be collapse of the wave function, then either you get 0 or 1. That is often called as to be uncertainty resolution, and so on. More generally, states can be defined as density matrix. So density matrix is basically a probability distribution over such pure states. So this one is a pure state, superposition state. And when you have many such pure states, you are not sure that which pure state perhaps that particular agent is in or a particular system is in. So you give a probability distribution over that, and that you call as to be density matrix. Now this rho thing here, density matrix, that is a very, very important thing for general modeling. So because in decision making, most of the cases we will not work with pure states. So we'll be working with more general states. So that is one thing. There are certain properties of this rho or density operator, as it is called. Trace of rho is always unity because there is probability conserving. And then rho square is equal to rho for pure states, rho square less than equal to rho for less than rho for non-pure states, and so on. Now, finally, I'd just like to say that in quantum-like modeling, one is the state kind of thing that we described, and the other one is that any kind of observable. So you want to observe certain kind of properties of that particular state, for example. Those observables are given operator representation. So everything in this Hilbert space is a kind of like operator representation. And that operator is often demanded to be a Hermitian operator, as Emmanuel pointed out that problem that in financial market modeling or decision modeling, at times, we do not have Hermitian operator representation. We have non-Hermitian operator representation. And that's a huge area of research. But in general, if you want to start, you can start with Hermitian operators. And Hermitian operators have real eigenvalues, as we know, so nice properties. And any particular operator like A, which is representing an observable, can be given a kind of decomposition into its eigenvalues and projection operators, which take that operator and project on that eigen subspace. So this X is the eigenvalue and EX is the corresponding projection operator, and so on. So that is what is done basically. Now, finally, what you then do is that once you set up these states and once you define the operators in the Hilbert space and corresponding observables, then finally you calculate the probabilities. So because ultimately basic quantum theory is all about calculus of probability. So you want to say that what is the probability that A will have a value X, one of the eigenvalues, given you start from a density matrix state of rho. and that is given as a trace formula. So trace of Ex multiplied by rho, where Ex is the projection operator and rho is the density matrix state to start with. Now, this trace formulation is also one way of expressing, which is again the Bond's rule. So square of the amplitude, remember alpha squares and beta square. That and this particular formula, they converge. So they are giving you the same results, but this is a trace formulation of the Bond's rule. And we should remember that Bond's rule, which is this one, is rather the unique and coherent way of calculating probabilities in a well-defined Hilbert space. So there's a huge amount of literature on this, that you cannot use any other kind of rule, because if you use any other kind of rule, there will be incoherence and kind of like various other problems, space-time structure will be violated and so on. Later on, then what you then do is that once you calculate the probabilities of certain outcomes, that is the most important thing to start with. The final thing would be that the next thing would be that to do some kind of dynamics of the modeling. So what you can say is that, well, phi t was my basic state to start with. That state might be belief state of an agent. That state might be, say, the strategy state of any particular player in a game, and how that evolves over time. So the dynamics comes in, and therefore for dynamics also you have different equations. They're often called as to be either Schrödinger equation, or if you don't like that word, some kind of density matrix equation given by Neumann and so on. Basically, you have this kind of things that phi t is exponential minus IHT phi 0, where this H thing here is nothing but the generator of the dynamics, which is nothing but the Hamiltonian. So the main thing for the dynamic modeling will be to calculate or to conceive of a well-defined Hamiltonian. And fortunately, there have been many suggestions given. Andre and Emmanuel has worked on that. And as I mentioned, Fabio Bagarello, a very important mathematician in this area, he has really come up with some suggestions of coming up with Hamiltonians, because that is a challenge. Because here it is the, the uniqueness of quantum-like modeling. We cannot just simply rely on physics, because in physics, Hamiltonians may look completely different. And in social systems, it is completely different. So that's a challenge here. Well, then let me then go into another interesting area, which is Bayesian networks. Now, certainly, you know that all of you who are experts in game theory, Bayesian network is a very well-known thing which has come up in the game theory. In Bayesian networks, we basically have nodes and directed nodes basically, and each and every node we are calculating some probabilities, conditional probabilities, and total probabilities. So say, for example, we have Alice and Bob playing a typical prisoner's dilemma game. So what is the probability that Bob will defect? So B equal to D, B for Bob, A for Alice, as stereotypical thing goes. So a probability that Bob will defect is equal to probability that both will defect plus the probability that Alice will cooperate and Bob will defect. So this is one total probability formula. And then you get the expansion of this, that B equals to D given A equals to D multiplied by probability A equals to D plus the counterpart of it. So that is the typical total probability formula that we use in Bayesian scheme. Now, the problem is that when we repeat the same thing to find out this total probability formula in a quantum-like modeling setup, starting from Hilbert space modeling, we get a very, very interesting additive term here, additive perturbative term here, which is often called as to be the interference term. Now, interference term comes from the notion of physics, but we don't need to really get into that. We just see that there is some interesting interference terms addition to this total probability formula. And here the literature is suggesting that most of the deviations that we see in the real life from the classical predictions of game theory, that might be somehow related to those interference terms. So those interference terms have to be explained better to see that why those deviations take place. For example, in a classical prisoner's dilemma game, First of all, we know that, well, if the two, Alice and Bob, are fully rational and there is common knowledge of rationality and there is no information asymmetry, everything is fully symmetric. In that case, certainly, there is a kind of dominant Nash equilibrium. We all know that is the defection equilibrium, and that is the dilemma of the game, because typical rational behavior giving rise to defection rather than cooperation. But again, in real life, what happens is that under uncertainty scenario, people do deviate from that kind of equilibrium behavior. Now, a Bayesian network would rather like to calculate those probabilities by using this formula, but then definitely going into quantum-like modeling, the same formula would have some extra terms. That is the interference term. And that is often known as to be the modification of total probability law, TPL. Andrei Krenikov and Emmanuel have very interesting papers on this also. So that is the main thing here. So what happens is that you start with this kind of a state, this kind of a belief state, Ket phi. So it is the belief state of, say, either Alice or Bob. And then you write up that particular belief state in this kind of a basis. So say Ket A1 and Ket A2 are the basis, just simply like 0 and 1. And these are the coefficients, P1 multiplied by e to the I alpha and so on. These are the coefficients. So this is something like alphas and betas in the last slide. And then what you do is that you use this projection postulate, as I just mentioned earlier, projecting the state into one of the basis states and so on. And then finally, what you do is that you come up with this kind of a formula. So in this particular formula, what we see is that with the total probability formula, then what is the formula that Bob will defect? B equals to D. That is equal to some coefficient outside multiplied by this whole thing squared, where this whole thing is like this particular state where both will defect plus the particular state where Alice will cooperate and Bob will defect. When you put them into this square as a whole, you will find that there are three terms coming up. One is the squared terms, which are similar to the classical Bayesian formula terms, but then you get some interference terms also, where once you break up this particular formula. Where alpha in this case is the normalization coefficient and normalization factor. Basically, then the whole question would be that how to calculate those interference terms. Now, I must say that there is a very good literature now suggesting that those interference terms are real. That is, for example, you start with real data first of all, and then look into the real data, analyze the data, and really find interference terms within that real data set. And then you try to map it with the kind of quantum-like modeling here. And here, what it has been shown, I will go to the reference page. If you can see that very interesting paper, which has come out just a few years back, where there's some heuristic rule which have been suggested to calculate the interference term, which is actually basically represented in terms of cosine theta terms, basically. So that is one application of one can say the quantum Bayesian nets. Why quantum? Because we are using this special probability calculus, and so on. It goes on. I will be very happy to share this PPT, but given the brevity of time, so one can do various other things. For example, not simply considering two agents, there are multi-agents extension of that. Or for example, the belief states of the agents can be in a way correlated to each other. So, in classical game theory, we have correlated games. So what can be the quantum-like version of that? So that kind of correlation, etc., they can also be calculated with the help of this mathematical modeling. There are ways of doing this, starting from this basic setup, bit of more algebra involved, etc. Now, finally, I would just say that there are many applications of quantum games which have come in. Say, for example, basically, now I'm going to the second part of it, where really you are designing a game. Remember that as of now, Hilbert Space modeling, quantum Bayesian network, they were basically describing people's behavior, describing game theory. But now if you really want to design a game to get quantum advantage, so to say, or to generate superior equilibrium, then you have to follow a bit more elaborate scheme. As I just mentioned that, players are like kind of sharing some physical resources, and those resources can be like quantum circuits, etc. And then they are doing certain kind of operations on those physical resources to create new states out of that. And then those equilibrium states which are created out of that, that can be more superior, correspond to a classical game counterpart. There have been a very strong literature in this evolving since 1999. Basically, in 1999, this particular paper came out, EWL. You can pronounce, all the names of this. They were a group of quantum information theorists, I think, and they suggested quantizing a non-zero sum game. So they were really using this kind of a setup for business dilemma kind of a setup. And they were showing that if you follow this quantum game design, then what may happen is that you can achieve non-defection equilibrium, or say a cooperative equilibrium, or superior equilibrium at one round quantum game even. So you don't have to play that game for multiple rounds. We know that in this classical game theory, cooperation may emerge if you played quite a few rounds, but here it is more efficient in that way. And so on and so forth. And it is very interdisciplinary as of now, quantum information theory coming in, market design coming in. There have been many papers written about to really conceive of a more, one can say, futuristic market economy, where, say, more digitalization will be coming in, more quantum computation will be coming in the market. And you see that in today's advancement of technology, these things are really not away from us. So maybe that within 10 to 15 years or 20 years, who knows, quantum computing might be commercialized. And if that is done, then certainly designing quantum game in real sense might not be kind of like out of chance. That's it. So finally, I would say, yes, finally, I would just like to get into this particular slide and stop here. You see that is a huge topic, so we cannot really go into too much of technical details for brevity of time. Here, I would just like to ponder a bit and see that what is there for policymakers, what are there for researchers, like mainly say JSGP for us, and also CEASP Center, Complexity Economics Center, where we are founding members. So actually, we are also interested to see that what quantum game theory or quantum-like modeling can really offer us. So first of all, I should say that, as Emmanuel rightly mentioned, that it might not be all about modeling. You see, modeling is one part. There's no doubt about that. For example, our next speaker, Thomas Hancock, he is a master in modeling, and he will be kind of talking a lot about modeling. But along with this, there may be something else. For example, there are certain features in human decision making, for example, contextuality, complementarity, etc., which goes deeper. And maybe that quantum-like modeling or quantum modeling, whatever you say, that is really throwing some light in that. And therefore, as a policy maker, if you really are into this kind of emerging field of behavioral policy making, then maybe it is better for us to really look into these quantum-like setups, because they are illuminating human decision making more. We know that behavioral policy making has really come up. It is basically based on behavioral finance and behavioral economics, but then you can add to this seminal contribution by quantum-like modeling. Because you see that quantum-like modeling ultimately is telling us that human decision makers might be non-Boolean in nature. So rather than Boolean, non-Boolean. And Andrei Trenikov, again, is one of the masters here, and he has worked a lot on this particular aspect. So it is not simply about modeling, and that might be very well related to policy making too. There are some very interesting applications already there. For example, there is an application on common knowledge formation. Again, Krenikov and others have worked on that. Going back to Oman's seminal paper, Robert Oman, we know that there is a kind of tendency of convergence of beliefs given the common knowledge assumption. So if you start with common priors and posteriors are common knowledge, then you cannot agree to disagree. But again, if the agents are non-Boolean in nature or quantum-like in nature, there may be some kind of extension of that theory. And why that is important, because that may really well relate to the things which are happening in financial markets all the time. In financial markets, we always see divergence of opinion rather than convergence of opinion. So maybe quantum-like modeling can really throw some light on that, and so on and so forth. There are challenges, of course. We have to interpret various things more carefully, as Emmanuel pointed out, a lot of interesting things. And also I should mention that with Professor Ghosh, one framework we developed, which is not fully quantum. So this particular framework, we have called it as a kind of classical Hilbert space modeling. In classical Hilbert space modeling also, it is like more in a way, more appropriate to decision making, because we can get rid of certain unwanted features. So that is also there, which we can talk about a bit more later. So these are the various things which are happening in quantum games and quantum-like modeling. This is a kind of small list of reference. Quantum social science, of course, it is like a seminal book right now, Haven and Krenikov. Classical optical modeling of social sciences. This one I worked with Patra Ghosh. This is the thing that I was talking about. We applied to prisoner's dilemma game also. And then there's this very interesting, only few papers I have just cited on quantum games. So that's very much it within a brief span of time. Otherwise, we might go on for a long time. So thank you very much for attending our special session on quantum-like modeling. 2 more speakers to come in. Please be there. So I'd be happy to take a couple of questions. Thank you very much. Shivangi? Okay, so Emmanuel, do you have any comment on this?
No, I think it's a very interesting talk, Sudip, and I think you've given a very good overview also of anything which is Boolean, non-Boolean, quantum games. I was trying to think EWL. It's were you talking about ISERTs?
Yeah.
Okay. Yeah, a growing area also.
Yeah.
Very interesting talk. Thank you.
Okay. So that's great. So please write to us over time. You can just mail me. You can just mail Emmanuel. We will be very happy to take any question. So let me now hand it over to Cheshta. Cheshta, please be ready with our recorded sessions. I just introduce the remaining 2 speakers. Definitely one is Dr. Thomas Hancock, who is an award-winning researcher at Choice Modeling Center, Leeds University, UK. They have used a lot about quantum-like modeling in very, very practical problem solving. For example, transportation choice problem. So that will be his main area. And again, some of you who are like more policy minded and more practical minded might take some inspiration from that research. And then I finally turn to Dr. Monireh Houshmand, who is based in Iran. She has worked with Dr. David Orell, David Orell being a mathematician based in Canada. And they have worked on quantum-like modeling for financial markets and economics in general. So that would also be quite interesting to look into. So I just hand over to Cheshta to run those links, and please be with us and ask your questions or whatever. Thank you.
Professor Patra, can you please stop sharing? Then I'll be able to share. Yeah.
Hi, my name is Thomas Hancock.
Professor Patra, can you please confirm if the audio and the video is clear?
I can hear. Emmanuel, is it fine? Yeah, Cheshta, you can go on.
Okay.
Leeds in the United Kingdom. Today, I'm going to be telling you about an overview of quantum-like behavioral choice models. First thing, what is quantum probability? Well, in the early 1900s, physicists demonstrated that the sequence that measurements were taken in affected the final observed values for physical variables. These variables were then defined as being incompatible with each other as measurements are non-commutative and cannot be made at the same time. This led to the development of a new theory, to the theory of quantum probability or quantum logic. And this was as a result of the breakdown of classical logic. So basically, typical methods could not be used to explain this finding. And now, of course, ordering effects happen all over, and in particular, they are a common phenomenon in choice behavior. So that makes it very relevant to choice behavioral modelers like myself. This has led to the development of quantum cognition. Quantum cognition is basically the fact that quantum-like models are gradually being introduced into psychology. And they aim to control and predict the impact of order effects. So for example, if I choose my travel destination, then travel modes, or do I choose my travel modes first, then destination? And I'll come back to an example of this later in the presentation. We can also use quantum models to essentially test the impact of behavioral nudges. So for example, if I ask someone how much they care about the environment before asking them how they're going to travel to work. And this nudge beforehand may change the behavior because they may want to look like they're making ethical decisions and therefore be more likely to make the greener choice if they're sort of nudged first. These models are effective in explaining a number of effects within cognitive psychology, including ordering effects, disjunction effects, two-stage gamble problem, etc. So can we also include these within a mathematical choice model? So firstly, a representation of a choice in a quantum framework. What does this actually look like? So here, what we've got is we're imagining that I'm choosing between traveling into York city centre or Leeds city centre. The two nearest cities to where I live. York is considerably smaller, but more touristy. There's more tourists there. Leeds is obviously where I am at university. Now, we have this Hilbert space here. And the Hilbert space represents a series of choices, not just Leeds or York, so where, but also how. So, for example, travel modes and when, so what time of day might I travel at. So a series of choices can all be represented within this one Hilbert space. Each choice scenario itself is represented by a subspace. So we've got a subspace for where, how, and when in this case. Each subspace is then created by a basis of vectors, so the different possible alternatives. So we have one vector representing each alternative. So here, this orange vector is the vector for York, the green one is the vector for Leeds. Now, this is a Hilbert space, and what this really means is that these vectors have real and imaginary parts. Now, of course, that's very difficult to visualize graphically. This currently looks like a geometric space with real numbers, but actually what would happen is that this is an imaginary space as well. So what happens when someone is making this choice? They have some beliefs. They might, for example, think that Leeds is easy to travel to Leeds, therefore it's going to be a comfortable journey. Or they might think there's more to do in York, therefore they want to go to York. And different things will mean that they will have some propensity to choose either Leeds or York. All of these beliefs are contained within this belief state. Now, then, because the basis vectors are orthonormal to each other, so basically we're assuming that you can only choose one alternative in this these case studies, then this collapsing of this belief state onto one of these alternatives can then also be the probability. So basically what happens here is that when a decision maker makes their choice, they go from this indefinite belief state to having a belief state that is mapped as the vector for York or the vector for Leeds. So a choice is made by projecting onto the vector representing the chosen. So the individual's new state is this chosen vector. So for example, I might choose York, then this is my belief state. So now, because these belief states, these vectors are orthonormal to each other, and the belief state has unit length, these can be probabilities. So we can see within geometric space, this is equivalent to Pythagoras' theorem, but in imaginary space, we can use complex conjugates here to ensure that we have firstly real projection lengths, meaning real probability values, and that's probability of an alternative can be defined as the modulus square of its amplitude here. So representation of two or more choices. For example, let's say we're now thinking about where to travel and also how to travel. So we've got the same case study here. We've got Leeds or York. We're going to choose to travel by the train or by car. Now, it could be that I first think, how am I going to travel? Now, previously, I maybe would have thought I'd travel by train, but now because of the COVID pandemic, I'm less keen to use public transport and I might instead choose car. Now, if I choose car, then I don't want to go and drive in a bigger city where there's going to be more congestion, more traffic, more delays. That means I might be more keen to choose York. So my first choice, choosing car, impacts the probability of me choosing York or Leeds. So basically what this is saying is that we have some initial propensity to choose either York or Leeds, but by choosing our travel modes, that's going to impact the probability of us choosing our destination. So in this case, that's exactly what happens. If I choose train, then I become more likely to choose to go to Leeds. If I choose car, then I become more likely to choose to go to York. Now, equivalently, we could have chosen where we are going first and then choose the mode. So maybe there's a particular event we want to go to, or maybe I've decided I'm going into work. I'm actually not working from home for a change. And I'm going into Leeds, and then I would choose the modes. And by choosing your destination first, that also is going to then impact which mode you choose. So how do we calculate these new probabilities? Well, if we suppose we know the original probabilities of choosing alternatives, so we have some way of defining this belief state. What we then need is some way to rotate through this Hilbert space. So we're going to change the amplitudes through some quantum rotation through this Hilbert space. So we require a quantum rotation matrix. This matrix is simply going to map the original amplitudes to new ones. So we've got these original ones in black, and we're going to move to these new amplitudes in pink. And we're simply going to use a matrix multiplication. Now, there's certain requirements for this matrix, which is a unitary matrix, which means that this will ensure that the new belief state will still be of unit length. So if I choose train, there's still a total probability of 1 that I will choose either Leeds or York. Equivalent if I choose car. So basically that's saying the total probability of choosing Leeds and York should be 1 and is 1. And that's because I stay basically on this radius here. So there's a couple of different rotation matrices we could use. We, in our work, have used two that works quite effectively. One is to define a rotation matrix based on some combination of Pauli matrices. The other is to use a Hamiltonian operator. So the Hamiltonian operator changes the belief state vector according to the dynamics of the Schrödinger equation. Now, this matrix H must be Hermitian, and this ensures that time evolution will conserve the normalization of the belief state, basically ensuring that the probabilities of the alternatives will sum to 1. So basically, there's these two different things we can do, and that will guarantee that we stay with in a proper probability system where the sum of the probabilities of choosing the different alternatives sums to 1. So final bit of theory here is that this change, this rotational change could instead represent a change of choice context. So rather than saying it's two different choices, one of them could be a slightly, I guess, implicit decision. So for example, I'm choosing between some status quo and some new policy. So some new policy has been introduced, I may like it or not. Now, it could be that I have an initial belief state regarding whether I think which one I'll go for at the end. But if I instead think, actually, are these policies, is this new policy ethically justifiable? If I answer yes to that question, then I'm more likely to say yes to the new policy. If I say no, then I'm less likely to choose that new policy. So in our data, we may have case studies where, or questions where we give to people where respondents see a clear change, an explicit change, but they may also not notice. So this would be, for example, if there's a behavioral nudge, it may be implicit behavioral nudge. So basically what we have here is that quantum models provide a nice conceptual account capturing the impact of behavioral nudges. So this is the example here, shows how that would happen. So what we have done in our work is to apply these models to a typical travel behavior model data. So we've got 3 applications here to go through. So the first one is from what is called the UK value of travel time data, first reported and described by Batley in 2017. There's about 3,000 individuals complete a survey. And in this survey, these 3,000 individuals face simple choice scenarios where they have to choose between 2 alternatives, which are described by 2 attributes, travel time and travel cost. So here is an example travel time, example choice task. Option 1 is cheaper, it takes longer. Option 2 is more expensive, takes less time. This is a classic example of a kind of question we'd ask people within our work, because this will give us an implied value of time, because we can measure the relative importance of cost to the relative importance of time. So that might mean, for example, we have an average willingness to pay of, say, £10, which would mean that most people would spend £10 to save 1 hour of travel time. And this sort of evaluation is used very often within transport policy making, planning type work, where they would say, for example, do we want to upgrade this railway line, and will it be cost effective to do so? So to establish whether it's going to be cost effective to do so, you need to work out whether people are willing to spend that bit of extra money to save that bit of time. And that's what these using these responses can help do. So basically what we have here is this these choice tasks that look at this, but there are 4 different configurations for how this particular task could look. So we could have cost on the left, time on the right, time on the left and cost on the right. We could then also have the cheaper option first or the cheaper option second. Now, there are context effects here in that the information you read first tends to get more weight. So, for example, I may be more likely to choose the first option, and I may be more likely to weigh the first attribute as being more important. And that's been shown quite often, that there is this bias towards the first alternative that people come across, or status quo bias, for example, also often happens. So how are we going to map between these 4 different contexts with our quantum choice models? So what we've got here is that the amplitudes for the different options is going to be some function of the cost and times. So basically, the probability of choosing the 2 different options originally is going to be based on some cost. their cost and their time. We then could have contextual shifts to the amplitudes. So for example, there's just an addition, and this shift would be an estimated parameter. So for example, if I change the order here, I will add some value to the different amplitudes. Or I could do a quantum rotation. Now, in this case, it could be implicit or explicit. We don't actually know whether the participant notices. So if you have a series of questions here, it's not necessarily clear that we wouldn't know if we've only got survey responses whether a participant has noticed whether we've swapped around the cost and time, or if they've swapped around the options here as well. So what our quantum model basically is going to do here is that it starts with this here as the base case. If we have the more expensive option first, then we'll apply rotation for the order. If we have cost second at the time, then we'll apply this rotation for the left-right bias. So we're going to have 4 different combinations here of not applying any rotations, here applying just the left-right one, applying the order one, or applying both. So depending on which choice task the person faces, depends on which rotation matrices we apply. So what we end up seeing here is that firstly, our quantum model does very well in comparison to the standard logit model, and also in comparison to decision field theory, which is another model that we've been developing. And it's a couple 150 units better log likelihoods, which is a very significant difference. And so we would have statistical evidence here to reject these models in favor of this one. Now, noticeably, if we use these shifts to account for the change in amplitude or change in utility, it would be in the logit model or preference value in the DFT model. We see these modest improvements in model fit, but we see the best improvement in model fit by using our quantum rotations. So basically what this is saying is that our quantum rotations are the best means to capture this behavioral nudge of swapping around the order of the attributes and the options. In our second case study, what we have is a case where we are choosing new transport policies. So our respondents, we've got about 100 of them, are given tasks such as this one. Do you support this new transport policy? So for example, imagine you are building this new road. It will result in 300 euros less tax, 20 minutes less travel time for you, but there'll be 100 more serious injuries on this road, and 5 more traffic fatalities on this road. Now, it could be that you think this is a great sounding policy because most people will benefit and there will be some injuries and fatalities, or it could be that you think, no, actually it'd be best to save life. So you get some different responses here depending on how much, what you think the sort of relative importance of these values are. Now, what we define here is that we define this as a taboo trade-off if a decision maker can choose to save money or time in favor of injuries or lives. So basically, if they say yes to this policy here, that would be a case of being a taboo trade-off. They have said it is worth having more injuries and deaths to save people money and time. So how does the quantum model here work? Well, I'm using this example that we had before, but now we've actually got this in terms of what this looks like for data. So we've got a status quo, we've got some new policy. And basically what we're saying is that people might be asking themselves, is this ethically justifiable or not? And that will change their likelihoods of choosing a new policy or not. So basically we're going to use this rotation for when there is a presence of a taboo trade-off. So if there is this possibly questionable trade-off, people are going to have to ask themselves, is this ethical or not? And this is an implied change, because we're not explicitly asking people, do you think this is justifiable or not? We're only theoretically suggesting that people might consider this. So we use a Hamiltonian operator to rotate through the space in this case. And what we see is that our model with the quantum Hamiltonian rotation results in the best log likelihood, so the best model fit. This makes the quantum outperform the multinomial logic model, which is a standard model, which previously did better before accounting for this rotation. So what this actually translates to is that the chosen alternative has an average probability of being chosen 63% in the first model, rising to 64% in the final model. So it doesn't sound like much, but 1% could be absolutely crucial. We can also add in imaginary numbers here, because previously our amplitude specifications, how we defined the values of the amplitudes, was not based on imaginary numbers. It was real numbers only, but if we add in imaginary numbers, we see a significant improvement in model fit in all cases here. So basically, we can reject the null model with only reals. That means we can move towards models with imaginary numbers, and that actually helps us predict predict behavior. Finally, what does this actually look like in terms of observed shares and model predictions? We see that quantum choice models accurately cover observed shares for the proportion of individuals who accept or reject new policies. And the average deviation from a model is only 2.5% in comparison to 3.3% for the MNL model. So essentially, 25% reduction here in the error. Our final data set, referred to as the Happy Wife, Happy Life data set, because people had to make a series of choices where sometimes it impacted their partner and sometimes not. So here's an example of an individual choice task. Here is your current alternative. Imagine that you've been offered a new job. It will take longer to travel, but you'll have more salary. Will you accept it or not? And you could also be indifferent. So these are the only things that change. We assume that the person is being offered the same, they're doing the same work. So they're only trading off salary for travel time really here. But in the second case, your partner also has a change in job. So we're looking at the difference between how you value your own travel time and how you value your partner's travel time. So effectively what's happening in our quantum model here is the same again, except this time we're really considering, do you consider your partner's preferences or not? And it might be that, for example, you are more likely to choose a new job if you do not consider your partner's preferences. But it could be that if you do consider your partner's preferences, you realize that having a longer travel time will have more of an impact on them, because you are not around the house as often, for example. And therefore, that would make you less likely to choose the new job. So what we find here is that our best performing model is, again, a quantum model, which does better than the random regret minimization model, which is a standard model that is used when you have the option of indifference. But what does this actually really mean? So what are our model outputs here? We've got a rotation matrix here, where the largest elements are on the diagonal, this entry here, this entry here. So that's basically saying there's most interference between options 1 and 2. And options 1 and 2 were the new option or status quo. Option 3 was the indifference. So what we observe here is that there's a shift towards choosing the status quo if also considering the partner. So approximately 75% chance rather than 70% chance of choosing the status quo. So some next steps and conclusions. Quantum choice models for notched choices would be something we'd like to do with revealed preference data. So this, what I mean by this is that It's actual observed behavior in the real world, not stated preference data in a survey. So for example, if you actually said to people, do you want to try and make a more ethical choice or a more green choice? How would that actually impact behavior? And then apply a quantum model to understand that behavioral change. We could do more extensions to repeated choice data, for example, learning effects. Can these learning effects be captured by quantum choice models? Large-scale moral data. So there's the moral machine data from MIT, which I would advise you to all go and have a look at. It's really interesting. That could be modeled with quantum choice models. And we could also make a return to experimental psychology. So how would the models we've developed perform for these settings? A few conclusions. Quantum choice models give good model fits. They're really simple to run and estimate, and I need to have more time to tell you about just how easy this actually is, but we use the Apollo choice modeling package in R, and there's only a few small changes from established methods already there to implement a quantum choice model. Rotation matrices appear to accurately capture changes in perspective, and they also work well from changing from best to worst choices, so basically from most preferred to least preferred. I just didn't talk about that today. And that's it. Thank you very much for listening. And I'm sorry I can't attend on the day itself. Please do send them to my email here, t.o.hancock@leeds.ac.uk, and I will get back to you as soon as I can. Thank you very much.
Okay, so Cheshta, I think you need to, start the video again for our next presentation, which will be our last presentation by Professor Monireh, based in Iran. We saw a very kind of emphatic presentation by Thomas, who is really a kind of like a excellent example of using Hilbert Space modeling for practical choices like transportation choices. So as we can see that from all of our attempts, that quantum-like modeling is evolving in quite a few areas. So it is in finance, in transportation choice, policy-making literature, quantum games, and definitely more deeper philosophical issues which Emmanuel raised earlier about decision-making itself, contextuality, complementarity, and so on. So finally, so please do send us your questions based on all presentations to our mail IDs directly. That would be great. So I think, Cheshta, are you ready with the next presentation?
Yes, Professor.
Okay.
Absolutely.
Okay, so I just introduce one thing that this particular presentation is also quite exciting. It goes into the usage of quantum probabilities in economics in general. David Orell, mathematician, and Monireh, they have worked on these areas quite a lot. And I have been in touch with David for quite some time. And great to see him here. Also, I found that he is online. So let's see this particular presentation, and then perhaps we can summarize.
Hello, everyone. I am Monireh Houshmand, an associate professor at Imam International University in Mashhad, Iran. The title of my presentation, which is a joint study with David Orell from Systems Forecasting, Toronto, Canada, is Quantum Propensity in Economics. Introduction. The assumption that people act rationally to optimize their own utility became the basis for economics in many years. However, cognitive psychologists have shown that this assumption is often violated. Therefore, economists began to adopt methods from behavioral economics in which so-called cognitive anomalies were accommodated by modifying the utility function to account for effects such as loss aversion or herd behavior. But a range of cognitive phenomena continue to elude behavior approaches because they do not conform to classical logic. This has motivated interest in adopting a mathematical framework based on quantum probability. Quantum probability is a set of mathematical rules to calculate probabilities of events in quantum mechanics. Quantum mechanics evaluates a probability P of x of a state x as the squared magnitude of a probability amplitude A of x, which is represented by a complex number. Its properties, such as non-additivity and non-commutativity, make it well suited to model uncertainty in decision-making behavior in social science, particularly in economics. Quantum decision theory is a framework for modeling and predicting human decisions to explain many behavioral phenomena which are unaccounted by utility theoretic approaches to characterize the rational-irrational dual behavior of real decision makers who evaluate not only the utility of the given prospects but also their respective attractiveness. Suppose that we wish to model the state of a person who is going to make a binary choice between two options. If the person is equally likely to choose either, then the situation is the same as for random coin toss. In general, the state could be modeled by the diagonal ray in figure A, where two dimensions are required because we want to capture the possibility of either outcome. If the ray has length 1 and we associate the probabilities of obtaining heads or tails by taking the square, i.e. the two norm of the projections onto the respective axes, then the probabilities add to 1 as expected. Let's suppose we apply a unitary transformation known as Hadamard transformation, which rotates S1, as you can see here, by 45 degrees clockwise. A cone in the superposed state of figure A will then be rotated so that it aligns with the h-axis, as in figure C, which means that when measured, it will be heads for sure. Another way to think about this is to recall that the initial propensity state is a superposition of two orthogonal states denoted H1, as you can see here in figure A, and T1. After being rotated, T1 leads to 3 here, T3, and H1 leads to H3 here. The T3 ray has a positive heads and a positive tails component. However, the H3 ray has a positive heads and a negative tails. The positive and negative tails components therefore cancel out, leaving only the positive heads components here in this figure C. This is an example of interference which again occurs because the two norm allows negative terms. Quantum computation. In a quantum computer, the coin toss would be modeled using the wave function ket psi of a single qubit, which is in a superposition of two basis states, ket 0 equal to 1, 0 and ket 1 equal to 0, 1, with the first representing heads and the second representing tails. We can then write ket psi is equal to A0, ket ket 0 plus A1 ket 1, which is equal to A0 and A1, where A0 and A1 are complex numbers with squared magnitude A0 plus squared magnitude A1 is equal to 1. When kets are measured in the computational basis, the possible outcomes are ket 0 with a probability squared magnitude of A0 and 1 with the probability equal to a squared magnitude of A1. Quantum gates which produce transformations are represented by unitary matrices, and 2 or more qubits are represented by tensor product. Quantum probability has been adopted in areas such as quantum cognition and quantum game theory because it naturally accounts for effects such as interference and entanglement. Well-known examples from the quantum cognition literature include the order effect, where responses to questions in a survey depend on the order in which they are asked. For the order effect, the usual way to think about this is in terms of a sequence of projections. A question A is followed by question B, and we assume that the questions have yes or no responses. Then the first responses is modeled by collapsing the state, shown by a diagonal red line, onto one of the two axes labeled a yes or a no, blue line, this one. That state is then used as the starting point for projection onto the B axis, I mean green line here. The probabilities of the possible outcomes when question A is asked first are as shown in this table. We suppose that the state vector, here the red one, is at an angle theta to the axis for A, and the axis for B are rotated by an angle phi to those for A. In this slide, you can see the probabilities of the possible outcomes based on the order effect. As it can be seen here, the order affects the probabilities. An equivalent representation of the mentioned measurement sequence is the quantum circuit shown in this slide. In this circuit, the input is ket 0, 0. A is r theta equal to cosine theta minus sine theta, and the next row sine theta and cosine theta, and B is equal to r phi, where phi represents the difference in the frameworks used to answer the two questions. The two qubits are then entangled through a CNOT gate, which is represented by the matrix XC. The operation depicted in figure yields the same output probabilities for the possible states as before. I mean the measurement sequences. Similar calculations can be made with the order of question reversed by inverting the CNOT gate so that the second qubit acts as the control and updating A as r phi and B as r theta minus phi. Each measurement in a non-computational basis is equivalent to applying a unitary matrix and then measuring in the computational basis. It follows that the circuit in Fig 1 here is equivalent to Fig 2 in the middle of the slide, where A and B are unitary matrices determined based on the given non-computational basis. We showed how this one qubit circuit with the two stage of measurements is equivalent to the 2-qubit quantum circuit depicted in Fig 3 here. The mentioned relationship holds when gates A and B are arbitrary unitary matrices, so the circuit is quite flexible and can be used to simulate any problem that can be described either by a sequence of projections as in quantum cognition or by an entangled state as in quantum decision theory. For the disjunction effect, gate A represents a context or a piece of information, while gate B represents a decision. For preference reversal, gate A represents a subjective context, while gate B represents an objective utility such as a monetary award. The circuit can also be used to simulate a version of the prisoner's dilemma, where gate B represents one player's strategy and gate A represents their ideas about the other player's strategy. Conclusion. To summarize, classical probability is the simplest kind of probability which is based on the one norm and involves positive numbers. The next simplest kind of probability uses the two norm and includes complex numbers. The reason this kind of probability is called quantum probability is for the historical reason that it turns out to be the right framework for quantum physics and is the basic of quantum computing. However, there is no reason we cannot apply it to other areas such as economics. Thank you for your attention, and please feel free to contact me if you have any questions.
Okay, thanks a lot. Thanks a lot. This was a very kind of crispy presentation with a lot of important points that we saw. And also, finally, I'd say that, the thing that perhaps Emmanuel also mentioned, and also I tried to mention, that there is a very strong field of quantum foundations, which is quantum Bayesianism or cubism, which also looks into, it is framed as a kind of more general decision-making theory. So therefore, as finally, as Monireh mentioned, that it is not really unthinkable that quantum probabilities can really be used for decision making, because cubism can also be thought as a kind of decision theory. So this shows that there are various interesting interfaces which are coming up, from economics to finance to psychology a lot. Cognitive psychology has been talked about a lot in this framework. And I should also mention one thing, as the last presenter also referred to Didier Sonnet and Yukalov. So they are like two gurus of quantum decision theory. So we were very honored to kind of have Professor Sonnetti last time from CASP Center, where we kind of held a conference on complexity economics and related areas. So I will really hope that we continue our, our partnership, our networking, and I will really hope that we will get Professor Emmanuel Haven and all the other pioneers in this field for other projects that we are working on from our center. So finally, I hope that it has been an interesting session with a lot of intriguing ideas. Thank you, David, also to be participant in this. David Orell, I've been interacting with him for quite some time. So let me give the final word to our organizer, Shivangi, Professor Shivangi Jindal.
Thank you, Sudip. So sorry I stepped away for a while in the middle, but I had a question after I listened to most of your talk. Are there or is quantum-like modeling applied to continuous games framework, or is applicable to where the because so far the presentations that I've seen have those action spaces which are discrete. So I was just wondering, like, and this is specifically because of my interest is in auctions. So,
Okay.
and the starting point of any auction game is that it has to be a continuous game, and well, bidding strategies are continuous functions. So,
yes, I will say that very recently there have been some attempts like that.
Okay.
So it is really not impossible to think in that way. Now you see that one very interesting thing is that in quantum physics, which is really not our matter here, there has to be like discreteness, and there has to be like kind of quantization.
Yeah.
But definitely, since if we play in the regime of intermediate, say kind of like semi-classical model or semi-quantum model, so there certainly there is an option of going for continuous strategy space. It won't be difficult.
So for that matter, like, you mentioned market design as one of the potential applications. I was wondering, like the classical markets that we have been studying about, the Cournot or Bertrand models of duopoly or oligopoly models for that matter, the strategy spaces need to be continuous. So
papers, models are coming up in that way also. So I think if Emmanuel would like to add to that.
I was thinking also about, if you look at arbitrage, right? It's the same thing, same situation, right?
Yeah.
So it's much harder, right?
Yeah.
It's hard.
Yeah.
Maybe Professor Orell knows more about it than I do. I don't know.
Yes,
Oh, I don't think so.
Hi, David, how are you? I think we are disconnected.
Oh.
I think I heard David, but very, very briefly.
Oh yeah, no, just that I didn't know anything about that area. Hello, hi Sudip. Hi Emmanuel.
Hi Dave. It's amazing that we have to go through India to meet.
Yeah, that's right. Yeah.
Yeah, so David and I were communicating over email for a long time, but we didn't meet. So this is the first time that we are like seeing each other in a way.
Yeah, that's right. Yeah, it's been a few years now. I missed most of the conference so far, but yeah, I really enjoyed the Emmanuel's and Sudip's presentation. And yeah, if there are any questions about Monireh's presentation, I think she did a great job of it. But if there are any questions, I'm happy to address them.
Yes, I think that we can send some questions to you directly on mail. Maybe we can get in touch in that way.
Yeah.
And also, I will request both Emmanuel, David, and all of us to, there is a very interesting session tomorrow also on complexity model, which is coming up, where Naresh should be moderating. Professor Naresh Singh, as Emmanuel knows, is the vice dean of our school. So please attend that section also. It might be quite interesting modeling and so on.
Sudip, when is it IST time tomorrow? When?
Yes, I think tomorrow it is Shivani.
6:30. Yeah, 6 o'clock. I think 6:30.
6:30.
6:15.
Yeah,
Yeah,
I will not be able to.
6:15 IST. That would be. Yeah.
I'm not going to be able to make it, unfortunately. But you will record it, right?
Yeah.
Yes, of course.
So maybe if David can make it, it would be great, because maybe there might be some interesting interaction there.
Yeah, unfortunately, I have a Zoom at 9:15 a.m. here, so that's your time.
Yeah. Okay. Great. I think we can conclude the session. I mean, so we are closing. Great. So we are closing the day for day one of the conference. It's 9:05 p.m. IST. So yeah, it's been a long day for all of us. So I hope we're having everybody's having a good time, and see you whosoever can make it to the second day. And again, a grueling length of presentations that we have lined up.
Thank you very much. Thank you.